I'll first introduce myself. Hi, everyone. My name is Joy Payton. I use she, her pronouns, and I am a data educator with Arcus. And today we are going to be talking about database normalization. Now, let me start by sharing, in the chat, there was already a link to the slides. But let me show you, you might see a different experience of the slides than I do. You might open it and see something like this or something like this. And so I want to show you, if you follow the link to the slides, the best way to follow along is by clicking on the little book in the upper right-hand corner of your screen, and that changes the mode. And so the presentation mode, we want to be slides. Oh, I'm sorry, we want it to be presentation. Presentation. And then I like to get rid of the table of contents. So I'm just going to hit the X in the upper left here just to hide that table of contents. And then if I decide I want to see it again, I can click on that again. So again, the buttons here that I'm using are the 4-line menu or the X menu on the upper left. And then there's a little button here that may be a speech bubble, or it may be a book, or it may be some slides, and you want it to be the presentation. So if you want to follow along, please follow along with this. Those slides are there for you, and they actually include my speaker notes. So if there's something that I said that you missed, everything that I'm going to say is in the slides today. So with that, let me find my speaker notes among all of these windows. Great. And just jump right in. So I did already introduce myself. Again, I'm a data science educator with the Arcus project in DBHI, which is the Department of Biomedical and Health Informatics here at CHOP. And today's talk is the second in a series of talks about SQL, that we are going to be offering over the next several months. And we're recording today's webinar, so please leave your cameras and your mics turned off until the question time at the end, just to preserve your own privacy. And we'll give some time at the end with the recording turned off so that you can ask questions and not worry about being recorded. If you do have questions that you want to ask during the talk, please feel free to put them in the chat, and I'll periodically take a break and look at chat to get caught up on questions that came along. So with that, let's go ahead and get started. So today in our webinar, we will be talking about why SQL data is structured in interrelated tables and why that can both be useful and can be a little bit frustrating or challenging for newcomers who are newer to working in SQL. We are not going to be doing any hands-on coding with SQL today, but in future sessions in the next few months, that will be available to you. So if that's something that's interesting to you, hang in there and you'll get a chance to code. But after today's session, we believe that you'll be able to do the following 3 things. You'll be able to explain the significance of one-to-many data relationships and how these relationships affect data organization. You'll be able to describe how a normalized database is typically organized. And don't worry if the phrase normalized database is new to you, we'll talk about that. And finally, we believe you'll be able to explain how data can be linked between tables, and in so doing, be able to define primary keys and foreign keys, which are 2 very important terms. We always like to acknowledge our authors, and it feels a little weird to thank myself as the author of the module that this talk is based on. But I do think it's important to acknowledge authors, and really importantly, we want to express gratitude to NIH for funding our data education efforts in an R25 grant, which is the project that gave rise to the source materials that we're going to be using as the basis for the talks for the next few months. Now, as an educator, it's really important, I believe strongly in interactive content, and we think that the best way for you to learn is to practice. So I am going to invite you to be active learners today. Again, we're not going to do hands-on coding, but we will have some short quizzes that come up. to help you check your understanding. And I'll also ask you to contribute your thinking about some questions I'm going to pose by typing into chat. So I'll warn you ahead of time that I'm about to ask for your participation, and I do encourage you to make the best use of your time and jump in and participate. So let's just do a brief review of last month's topic. So last month, our topic was demystifying SQL, which was a brief introduction to what SQL is for people who have never heard of it or who have heard of it but know very little about it. And I'm not going to go into depth in reviewing last month's session. We will have a link soon to the recording of last month's session, so keep your eyes open for that. But in terms of review, I want to hit on a few important things that we talked about in the last topic. First, SQL, SQL, you can say it using the letters or by the word SQL. That stands for Structured Query Language, and it is a language used to request data to make queries from a relational database. And so that brings us to the question, what is a relational database? The next bullet point speaks to that. Relational databases are ways that we organize data in tables that are interrelated. There might be, for example, a subject ID that appears in several different tables, and that shows the relationship between those tables, and that's what makes a database relational. And finally, tables have columns, and sometimes we call columns fields, and tables also have rows. That's what we went over last month. And again, today we're going to talk about how data is organized in these tables in databases and why it is that you have to use multiple tables, not just one, but multiple, for just about anything interesting that you want to do with data from a database. So often you have to combine data from 2 or more tables to get the information you need for your work. And this can be frustrating if you're accustomed to getting a CSV for analysis. You're used to getting just one table, one spreadsheet, and suddenly having more than one table to deal with can be challenging. So I want to start by giving a use case that illustrates why getting data from multiple tables is important. And then we'll talk about why it's not practical to store medical data in a single table. So I'm going to pause and let me just include this link because I know this is small on your screen so that you can get a chance to look a little bit closer up. Oh, thank you so much, Rose, for adding that link. So give you a chance just to look at that real quick. All right, so if we look at these tables, we can see that we've got multiple tables that describe a research study about depression. So let's say we're studying depression in research subjects who live in different areas. And you have lots of tables of data, maybe many more than we're showing here, but we're just going to show a sample here. So we have one of these tables that has demographic data about our subjects. That's very typical in a research study. We also have a table that holds depression scores for subjects. So this is, it looks like it's maybe a 4-question psychometric scale. And this 4-question scale has the 4 questions and then a total depression score. And that table is called depression scale right here, depression scale. And then we have a third table here called subject address. And so I'm going to ask for your participation now. So perk your ears up and get ready to type into chat. Let's posit, shall we, that your hypothesis is that people who live in certain zip codes, maybe zip codes that experience more socioeconomic challenges, those folks have higher rates of depression. So if this were your hypothesis, that zip codes were linked to depression, which fields, which columns would you need to look at in each of these tables? Let me zoom in a little bit and scroll down. Maybe that'll make it a little bit easier for you to see these column headers. What columns would you be interested in looking at in each of these tables? And when you have an idea of what you think you would want to look at, just share that in chat. Great. I'm in agreement with what a lot of people are typing in. Subject ID, depression total, depth underscore total, and zip. Yep, very good, Darcy. You're using subject ID to link information from two different tables. Fantastic. So I also agree that if you wanted to see if your hypothesis has evidence to back it, you would need to combine data from tables 2 and 3. So you would need the subject ID and the depression total score from table 2, and then from the addresses table, you would need the subject ID and the zip code. And that's what you would need to work with. And so what you might want to end up with eventually, right, as your sort of last thing before you do statistics, would be a single table of results that looks like this, where you have 3 columns. The things that you really care about, the subject ID, the depression total score, and the zip code. And that way you have all of your data in one piece, in one place, and you can look at the relationship between depression score and zip code. And you may be asking yourself, and you may have asked this of people who've delivered data to you in the past, hey, why don't you just put everything in one table to start with, and then I can just select the columns I care about? Why are you separating things out into all these different tables? Because after all, we really want to get to this final model where we have 1 row per subject and everything we need in these columns, and that's how we apply statistical tests usually. So it would be great if we could start that way with just 1 table, ideally 1 row per patient or 1 row per subject with everything we need. And if you're used to getting a CSV that looks like that, and then somebody comes to you and says, no, we're not going to give you the data like that. We're going to give it to you in a bunch of different tables. That can be, again, it can be frustrating. It can be challenging. So I want to explain why this happens. And to explain normalization, which is how we structure databases, we first need to talk about one-to-many data relationships. So let's talk about one-to-many data relationships. There's lots of examples of this in lots of different domains. So medicine is chock-a-block with these one-to-many data relationships. So if we consider in the hospital, 1 patient might have multiple encounters on different dates, and 1 encounter might include multiple orders for procedures or medications, and 1 medication order can give rise to multiple medication administrations. You can think of a lot more examples of one-to-many data relationships. Or if you're thinking about a retail website, 1 customer might have multiple addresses for billing or shipping or both. 1 customer probably has multiple orders. Each order has 1 or more items in that order. So there's lots of one-to-many data relationships in which 1 X is related to more than 1 Y. And these can be hard to accommodate in a single table with all of the data included. So let's exercise our imagination a little bit. And so imagine that you have an online store. Congratulations, everybody's shopping for the holidays. And so you're going to design a table that holds order information. And you would like each order to be on its own row, and everything about that order is in 1 row. And so maybe you start with 5 columns. So you have your customer ID, maybe their address, and item 1, 2, 3. And then you realize, oh, I'm going to need a lot more columns because people are going to order many items. So then you make 50 columns or 100 columns. And you realize there's no way to predict how many columns you'll need. What if somebody orders 200 of something? Designing your database to accommodate everything in 1 row is really challenging when you don't know how many columns you'll need. And most of the time, orders are actually pretty small, a handful of items, 2 items, 4 items. So you have all these empty cells. If you have 100 columns to accommodate big orders, but you have all these empty cells, that's an inefficient way to store data. So that can be very challenging when you're designing data. So one-to-many is tricky. So I'm going to invite you to consider this question. And if you have this slide open, you can sort of click on this. I don't have a poll ready for you, unfortunately, this time around, like I did last time. But think about which of the following relationships, oh, actually, perfect. Thank you so much, Rose. Which of the following relationships are likely to be one-to-many? And please go ahead and select those for us. Exactly. You are all right on. I see a great pattern of responses here. So we do hope that any gym member will have more than one recorded workout. That is the hope anyway. So that relationship is one-to-many. But a particular street address is at one location. So it is going to be related to a single latitude and longitude. So that's not a one-to-many relationship, that's a one-to-one relationship. Now a patient can have multiple providers, so that's one-to-many. And providers can certainly have more than one patient. Let me click the show answer here. Providers can certainly have more than one patient. So you can really call the relationship between patient and provider many to many, right? It's certainly not one-to-one. And finally, and this is a bit silly, and in the last meeting, somebody pointed out that I think it was the Harrisburg Iron Pigs or something like that. Apparently there is a baseball team, professional baseball team, that has at least 2 mascots. However, I would argue in general, most times, a baseball team should have at most 1 mascot. So that is a one-to-one and not a one-to-many. I did not mean for that to be a trick question. I am not a huge minor league baseball nerd, but I learned something in the last session. All right, thank you so much. All right, so let's keep moving. And let's talk a little bit more about one-to-many data in medicine. And sort of think about our fictional multi-site research study. And I'm going to scroll and I'm going to sort of make this a little bit smaller because I need you to see the subject IDs. And again, this may be small, so I'm going to just put the link to this slide in chat in case it's hard for you to see in your screen. Oh, Harrisburg. Oh, perfect. The Iron Pigs and Harris. See, I'm learning stuff all the time. So if you look at this, and I know, again, this may be small, but I want to make sure that you have access to see the subject IDs. You may notice some one-to-many data relationships here. So I want you to look at the subject IDs here and tell me, what one-to-many data relationships do you see? And type those into chat. When you feel like you've seen a one-to-many data relationship, let us know what you see. And are there one-to-many data relationships that we see in this data? Excellent. Yep, Eloise noticed that there's a subject that has more than one address. That's not that unusual, right? Our subjects move. And especially if we're studying something like geospatial risks for things like depression, understanding what people are doing with where they move to is really important. So we want to record that. Yep. So at least one subject has more than one depression score. And again, this might happen. We might have repeated instruments that we give multiple times. Especially if we're studying a chronic disease, we might have patients or research subjects take a measure multiple times. So there's several one-to-many relationships. And this is, again, pretty realistic, right? If we think about the way our patients move and they retake things and they have multiple appearances, multiple encounters in the hospital and things like that. So if you were to think about combining this data with its one-to-many complications, it could be challenging. But people do ask us to combine data in challenging ways. And especially if you're, let's say, a research coordinator or a research assistant, a PI might ask you, hey, can you combine this data for me? It's in 2 tables and I need it to be in 1 table so I can, push it through statistics. How would you actually accomplish that? So I want to invite you to consider just combining these 2 tables. So table 1 is our demographic data, where we have information about things that generally don't change about our research subjects. When they were born, their sex, their race, right? So we have that demographic table, and then we have their depression scale. So you might even want to just sketch out, if you have a pencil and paper in front of you, kind of what that would look like. What columns would you have? Would there be any repetition? What would that look like if you combine table 1 and table 2 here? How many rows would you have? Would you have any empty cells, maybe? Do you see any issues, any problems? Maybe you see that there's a subject that appears in one table, but doesn't appear in the other table. What do you do with 86234, who appears twice? What does that mean? Well, this is what I think this combined data might look like. Is we have the demographic information in the first few columns, and then we have the depression inventory. And this looks pretty clean, but I do want to point a few things out. One thing is that the demographic data for a given subject is the same each time they take the depression inventory. So no matter how many times they take the depression inventory, their date of birth is the same, their sex is the same, their race is the same across all of these instances, right? So that means we're repeating several columns of data multiple times. And here it's just one subject, it's not a big deal. But for a more realistic data set, you might have 20 subjects repeating 2 or 3 or 5 times. And that could be a lot more rows of repeated data. And one of the issues that can come up is, what if we realize a given subject, we put in their date of birth wrong? So we have to correct it. And that means we have to go in and correct every single time it appears, right? And so because we've combined this data, that means their date of birth doesn't just appear once in a demographics table, it appears multiple times in this shared data. So that can be challenging. And we also have a partial row here. So we have a subject 93452 that we have some demographic information on, but they have not, at least not yet, taken a depression inventory. Again, it's not a huge deal. It's a few empty cells, but it is a bit inefficient. So that's combining 2 tables. We found a couple of small problems that could crop up and cause issues. But let's say we really wanted to press through and say, please combine all 3 of these tables into one data set. And what would that look like? And this is really challenging, and people do ask for this. So imagine that your PI or your boss or somebody, a colleague in your department says, hey, I'm not used to working with multiple tables. I need this just to be in one CSV. That's what I'm used to working with. So can you please just combine all of this data? Because I'd ideally like to have each subject just on their own row and everything we know about them across that row. Can you just organize the data that way for me? Which seems fairly reasonable. But what are some of the problems that you would run into? What are some of the questions that you might ask this person to clarify what they wanted? Or what are some of the problems you would run into? So again, I'm going to invite you to be brave and type into chat some of the things that you think might be problematic about combining data across these 3 tables: demographic, depression scale, and subject address. What are some of the issues there? Oh, Eloise makes a really good point about weighting data, right? What if you're over-representing a given patient, right? This patient has 5 depression inventories. Are we going to say we have 5 times as many patients from this zip code? Not necessarily, right? That could represent just one person. Very important. That's one of those sort of hidden things. Yeah, there's definitely repetitive values when you're trying to combine across these three tables. Exactly. Jason makes a very good point. If you want one row per subject, you need to differentiate repeating data. So maybe you have depression score 1, depression score 2. And each of these is actually 5 columns, right? Because it's 4 questions and then the total. So you're going to have 5 columns for the first administration, 5 columns for the second administration. By the way, how many administrations did we say are the limit? Is there a limit? Is it 10? Is it 50? Do we know? Right? I can't really plan how to shape my data unless I know how many. Similarly for addresses, we may be able to enforce that you only get 2, you get a pre-test and a post-test for the depression inventory, and we can enforce that. We can't really enforce how many times someone moves. So are we going to have address 1, that set of columns, address 2, that set of columns, address 3, that set of columns, all the way to address 15? What if this is a longitudinal study, right? This is really, really challenging. So it's hard to know ahead of time how many columns we need. And so maybe we make enough room for 50 addresses. Well, that means, again, we have a lot of inefficiency because most people have one address, right? So we're wasting a lot of space. And then if we need to do some analysis on zip code, we have 50 different columns that have zip code that we have to look in, right? Not just one column. So it makes analysis very challenging. So in short, what I hope that I've done is manage to convince you that if we take all the data we know about someone and try and force all of that into a single table, we have a lot of problems. And if you walk away from this knowing just that, that is fantastic, because I know that a lot of times people are asked to do this. Please combine this data into one row per subject. And being able to explain why this is very difficult can be challenging to explain. So if you walk away just knowing that multiple tables is usually better than one table, then I feel like my job here is complete. And so we're going to talk a little bit about normalization and why normalization, kind of what it is. We talked about why we need it. The one-to-many data problem is the big reason why. And so we'll talk about normalization in the next slide. All right. So on your screen, you'll see a little bit of behind the scenes info, and that is only if you're super interested in this topic. For most of us, myself included, we don't need this level of detail, but if you like it and you want to learn more, by all means, check it out. But the TLDR, too long, didn't read. The short version is normalization is a complex topic in information science. People do dissertations on this stuff, and there's various levels of normalization. We're not going to talk about what the different levels are. We're just going to talk about kind of what it looks like. And if you want to learn more, please, by all means, go into depth. It's very cool and interesting. But basically, in a normalized database, we separate data into tables. And these tables represent different logical concepts or entities, like an address, or a patient, or a medical device, or a medication, right? And we tend to only include in these tables the data elements that have one value that is relatively stable and won't change. For example, if I'm thinking about a medication, the generic name of Motrin is not likely to change, right? In the case of a device, a medical device, it has one barcode sticker on it, and the chances are that barcode sticker is never going to change, or maybe it'll change once in 10 years. It's a very stable code, so that adheres closely to that. A medical procedure will have one billing code associated with it. You get the idea. These are singular data elements that are pretty unchanging. And we might exclude from these entity tables things that change frequently. So for example, a patient might have multiple insurers, and their insurer might change multiple times. So who you're getting your insurance through does not adhere as closely to you as an entity as like your date of birth, which is really constitutive of you. It really adheres closely to you. Who's insuring you can change. It can be multiple things at different times. So we're not going to include that in the patient table, for example. And importantly, in these entity tables, like a device or a patient, we're going to include an ID, and these will uniquely identify each patient or each device or each provider. So it'll often say device underscore ID or patient underscore ID or provider underscore ID, something like that. So those are entity tables. So let's talk about these uniquely identifying IDs. If we think about a unique ID that can only occur one time in a given table, that is called a primary key. So a primary key is an identifier that is linked to one and only one row in an entity table, right? So for example, the patient ID. Patient ID 12345 appears only one time in the patient table. It cannot appear more than once. SQL won't allow it to appear more than once, right? A given patient ID links to one and only one patient. That patient is listed one time only in the patient table. That's a primary key. Same thing with medication. If you have a list of all the different medications that we can prescribe or give to our patients, ibuprofen 250 milligram caplet is going to appear once and once only, and it's going to have a particular ID, and it's only going to appear once. If you already use SQL, it is helpful to know that SQL does enforce this. If you say, hey, by the way, this ID is a primary key, it will not allow you to accidentally re-add that ID to another patient, let's say, or another medication. It'll prevent you from making that mistake. All right, so that is a primary key, and we can see here that it says PK, and a lot of times there'll be a little hint, either like a key, a little icon of a key, or the letters PK, or it'll say a primary key to let you know when you're looking at these tables that you're dealing with a primary key. And then we have interactions. So I said, oh, I wouldn't include insurance information in a patient table, but we do need to know about insurance, right? We need to know who's insuring whom at what point so that we can get paid, right? And that's talking about interactions between entities. So between payors and patients, there are interactions where this payor is responsible for this patient for this time period, right? And there's other interactions. So the one that I have on the screen is medication order. And medication order, you could think of as an interaction between a provider who makes the order, the medication that is ordered, and the patient that the medication is for, right? So there's at least three entities that are involved in this interaction. And you can see it has its own primary key here, but it's got these other IDs that don't have PK beside them, and we'll talk about maybe why they are or are not primary keys. But there are other IDs that say, by the way, it was this medication, this patient, done by this provider. So let me ask, I'm going to invite your chat again. Is Pat, P-A-T, patient Pat underscore ID in this table that you see on your screen, is this a primary key? Yes or no? And why? Why do you think it is, or why do you think it's not a primary key? All right, I have some no's. Very good. Yep, there's multiple instances. So Daniel says, I can see like 1512, that patient actually repeats, right? But importantly, Juliana points out a patient could have multiple med orders, right? Most patients do have multiple med orders, so it should not be unique, right? You might have 3 medication orders and 1 hospitalization, and then 2 years later, you have another hospitalization. In that encounter, you have 5 medication orders. So you as a patient appear multiple times. You can't appear once and once only in a medication order. Good job. And similarly, what about med underscore ID? That's the medication ID. Is that a primary key? It's not a trick question. The med ID, similar idea. Similar idea here. So I have some, yes, it's a primary key. No, it's not a primary key. I can understand why both answers are out there. You might say, well, Joy, these are all unique values. 1, 2, 3 appears once, 3, 4, 5 appears once, and 9, 2, 3. There's no actual repetition. So it's a primary key. False, unfortunately. It's not a primary key because we do have to allow for repetition, because ibuprofen is going to be prescribed 500 times this week, right? A given chemotherapeutic agent is going to be supplied to 3 or 4 different patients across the course of a year, right? We have to allow medications to repeat. So even though we don't witness any repetition right now, doesn't mean that repetition might not be necessary later. So it's not a primary key. And the same thing is true for provider ID. Obviously, providers are prescribing medications, if you're a hospitalist, all the time to patients, right? So it needs to be able to repeat. So if these are not primary keys, what are they? We call these foreign keys. So foreign here means originating in a different place than here. So patient ID, this identifier here, this did not originate in this table. It did not originate in medication order. It originated somewhere else in the patient table. And in that table, it is a primary key. Here in this table, it's not. It's just referring back to another table. Similarly, med ID is a foreign key. It originated somewhere else. And if we want to find out more about this medication, we can go to that table that it originated from, the medication table, and look up, what is med 123? What's its generic name? What's its brand name? What is its drug classification, right? So we can get details by going back to the originating table. Now, this next slide, if this kind of image helps you, fantastic. If this feels confusing, please don't worry about it. This is called an entity relationship diagram. And this shows the relationship between these tables. So at the top, you can see that there's 3 entities that we're talking about: provider, patient, and medication. And you can see that they each have an primary key, a PK. So it looks like the provider ID is the primary key for provider table, and PAT ID is the primary key for patient table, and med ID is the primary key for medication table. And those reappear down in the medication order table as foreign keys, right? And this just shows how these tables are related to one another. So if that helps, if you're a visual learner and that's helpful, fantastic. This is confusing, ignore it. It's not that important. All right. So the next 2 slides, I'm going to sort of fly through because I think you get it. I think you understand normalization. But I want to talk a little bit about fixing errors in your data. So we have an example here at a supermarket. When somebody set up the point of sale system, they misspelled orange juice. And so now we have to correct that error. So this is a non-normalized set of data. This is trying to get everything on one row. Every order is one row, so we have 50 different columns. And the misspelled orange juice could appear in item 1, item 2, item 3, item 4, item 5, all the way to item 49, item 50. And it could appear in every single row. So we have to look practically in every cell to find our misspelling of orange juice. All right. So that's one way of organizing data, and think about the effort that would take to correct something. And here's a normalized way of looking at this data. Yes, it's in 2 tables, which may be, again, a growth area. It may be something that you're not accustomed to. But importantly, our orders here are described in a table, and we have this order items where we have an order ID, and we have multiple rows. For this order, we sold this item, and this item, and this item, and this item, and this item. And we only have one place where the misspelled orange juice appears, and that is in the items entity table, right? So we just have to figure out which ID is orange juice, and we just change it in that one place, that one misspelling. So when we think about complex medical data, and somebody misspelling a name or getting something wrong in a problem list, or somebody needing to update their gender identity, you can imagine that it's much easier to correct and update data when it is in a normalized arrangement like this. Any questions about anything we've talked about so far? I've just sort of been holding court, so let me pause and see if folks have any questions. All right, so let's sum up where we are at this point. If you still have questions, keep typing, drop them in. But to sum up where we are so far, the theory of how to organize data for speed and for efficiency and ease of correction, that's a really complicated space. But it's enough for now to understand that data in these relational databases are fragmented into various tables that represent concepts or entities. And this process of breaking up the data and fragmenting it in this way is called normalization. And normalization is really important for keeping our data efficient, reducing complexities of not knowing how wide to make a table or having lots of repetition, and it makes correcting data a lot easier as well. All right, so I think we have another quiz coming up. Oh, I don't want to show the answer. Let's see. All right, well, the answer's up there. But there's another quiz. So here's a question. Why is data normalized? Why is data normalized? Clearly the answers are up there, but give it a think anyway, and think about how you would answer. Yeah, you're exactly right. So the reason for normalization is not that relational databases can't handle wide tables. Relational databases can certainly handle very wide tables with lots of columns. That's not a problem. Rather, the reason why we normalize data is that the kind of rich data that we store in these relational databases is just not right for storage in a single table. And that's because there's lots of one-to-many relationships, and that means that using multiple tables, one for each kind of concept, makes more sense. Because there's lots of repetition in data, right? When a normalized model is used, when data is fragmented into these entities, these concepts, things get a lot easier when it comes to correcting data, maintaining data, and analyzing data. So that you can look for zip code in a single column and not your first zip code, your second zip code, your third zip code, your fourth zip code, your fifth zip code, right? Looking in one place. Let's add a little bit of vocab here. So we already talked about primary keys and foreign keys. So I'm going to add the term join keys. And I don't often just read slides aloud, but that's what we're going to do here. Fields that appear in two or more tables within a database are also sometimes called join keys because they can be used to join data from the two tables into one set of interrelated data. And these join keys we can break down into primary keys, which are unique within a table, and foreign keys, which are not unique, but they come from and they can be traced back to tables in which they are a primary key. It can be useful to know that the phrases primary key and foreign key originated in SQL, and they're important to know if you work in SQL, but you might hear them being used in other environments as well, right? So let's use the student ID as the primary key. You might hear even about let's say a CSV or something like that. People use the phrase primary key outside of SQL sometimes as well. All right, let's bring up another quick quiz. I don't know why these are showing the answers already. I apologize, friends. There we go. Well, shucks. So here's another quiz question. So which of these fields is likely to be a primary key? You can avert your eyes But which of these keys is likely to be a primary key in this procedure table? Is it procedure ID, patient ID, date, provider ID? And I should explain that this procedure is a given procedure on a given day. Given procedure on a given day. Excellent. Yep. This is a table about procedures. Procedure ID is likely to be a primary key. But we know that patient ID certainly cannot be, because a patient might have more than one procedure, right? And a provider might give more than one procedure. So they certainly cannot be primary keys. The date is just a date. It's not going to be unique, and it's not an identifier. It's a date. So that's not a primary key. So it's likely that procedure ID is a primary key. We might need to understand a little bit more about this table and how it's used, but that's the most likely answer. All right. If we look at foreign keys, what are the fields here that are likely to be foreign keys? And again, apologies, I must have a caching issue because the answers are coming up for me. And if you guessed patient ID and provider ID as foreign keys, you were right. This seems very likely. Even without looking at other tables, I can just sort of use my logic to say, these are procedures, and it's referring to a patient ID. I bet that patient ID is a foreign key, and it's referring back to some other table that describes patients. Similarly with provider, I bet there's a provider table, and it has provider 1, 2, 3, 4, 5, and the provider name, and maybe the provider's department or division, and what their role is, etc. And so those are likely to be foreign keys. Again, date is not a key. All right, fantastic. All right, so we've reached the end of our materials here. So let's do a quick review. Normalization breaks up data into tables that represent entities, like patient or medication, and tables that represent interactions between entities. And data is organized in such a way that the number of columns is predictable. We don't have to figure out how many sets of addresses we need to accommodate horizontally. No, the number of columns is predictable, and data repetition is largely avoided. IDs might repeat, right? They end up getting repeated a lot. But the data underneath, like zip code or the spelling of someone's last name, or the description of a medication's mechanism of action, that stuff is not getting repeated. Entities are logical concepts like patient or medication. And each of these entities has specific aspects that adhere really closely to that entity. Like as a patient, I have a date of birth, or as a medication, maybe there's a class that this medication is always going to be in this class. Class is not likely to change. A primary key is an identifier that contains a unique value for each row in a table, so it will not repeat. So an item ID uniquely describes the item in an items table in the supermarket, and it won't repeat. A foreign key is an identifier in a table that makes reference to some other table. Foreign means it originated somewhere else. So it's originating in some other table, and it's a primary key there, right? So in our medication orders or our procedures table, our patient ID refers to the patient table. And it gives us a little hint and a pointer to say, if you want more information about this patient, look up 1, 2, 3, 4, 5 in the patient table, and you'll get everything you need to know. And together, primary keys and foreign keys are called join keys. And finally, an ERD, an entity relationship diagram, is an illustration of how different tables in a relational database are related. These diagrams often include details about join keys, and they show, again, how tables are interrelated and how you can sort of track back clues from one table and another table. I've got a few resources here for you, and I'll actually just copy and paste that as is in the chat, so you have access to that. Zoop. There we go. And finally, if this was useful to you, we have a number of SQL webinars like this coming up. So this is our second presentation of December. So our topic of December was database normalization. In January, we'll be tackling SQL basics. And you will finally get to do some hands-on code, which is exciting. February, we'll start doing some more complicated things with intermediate. And then in March, we'll talk about joining data from two different tables. And so we'll add the link to the website where you can sign up for all of these webinars. And finally, about these slides. So these slides were created with LeaScript, which is an open source markdown parser. And it's really aimed at creating educational content. So if you want to go back and look at these slides, the link to the slides, again, is in the chat. And all the speaker notes are also there. So if I click on this speech bubble and I go to slides, you can actually see my speaker notes down here below, right? And I could even hit the, I could even have them spoken to me if I wanted to and hit play and have them read aloud to me. All right. So that is available to you. You can also look at the textbook way, and you can see that the speaker notes appear sort of below, right? So everything that I've said and explained is also available for you in these slides.